Thank you all for being here. It's our second press conference of the day, Monday, June 9th, at the 246th meeting of the American Astronomical Society here in Anchorage, Alaska. I'm Kerry Hensley. I'm the Deputy Press Officer for the AAS, and I'm being assisted today by AAS Media Fellow Lexi Galt, as well as AAS Press Officer Susanna Kohler. Oh, I just realized, there we go. Surprise, we have someone online. So press releases, presenter slides, and the briefing video from this morning are all available in the press kit online, so you can look for those materials there. Press releases associated with this afternoon's briefing will be posted in the press kit as well as being posted to the Slack channel. So I'm going to give a brief overview of the ground rules in case this is your first AAS press conference. This press conference is being live streamed on YouTube, and it will be archived on the AAS Press Office YouTube channel after the end of the day. I'm going to give a brief introduction to the topic, and then we'll hear from our panelists in the order in which they're sitting here, with one remote panelist joining us. Then at the end of all those 5 presentations, we'll go to Q&A. So no separate Q&A for the presenters after their presentations. All right, so this afternoon, we're going to be hearing about a really broad range of discoveries. This is the From Molecules to Molecular Clouds, Discoveries in the Milky Way press conference. First up, we have Gabi Wenzel from MIT and the Center for Astrophysics, Harvard and Smithsonian, speaking on If You Like It, Put More Rings on It, Discovery of Interstellar Cyanocoronene. Then we'll hear from Atul Mohan from NASA Goddard Space Flight Center and the Catholic University of America, speaking on the discovery of the elusive radio burst indicators of massive eruptions in a young active star. Then we'll hear from Tahina Ramiaramanantsoa from Arizona State University, speaking on the spotty surface of the blue giant Xi Persei. Then we'll go to our remote presenter, Peter Craig from Michigan State University, speaking on a map of the outer gas disk of the galaxy with direct distances from young stars. And finally, we'll hear from Wanggi Lim from Caltech and IPAC, speaking on the SOFIA Mid-Infrared Giant H2 Region Survey Galactic Center. So with that, we will turn things over to our first presenter.
Okay, great. Thanks for having me. I'm Gabi Wenzel, a research scientist at MIT and the Center for Astrophysics, Harvard and Smithsonian. And I'll present on our recent detection of interstellar cyanocoronene. You can see its structure here. And this is a 7-ringed polycyclic aromatic hydrocarbon, or pH, or PA for short. The role of pHs on our favorite planet, Earth, is kind of detrimental. They're pollutants produced in incomplete combustion processes. So anytime you have a barbecue this summer, you see a car exhaust or like any wildfires, you can see that pHs will be blasted into the atmosphere and possibly also in our lungs. pHs are pretty toxic and carcinogenic, so we actually really don't like them so much here at Earth. In space, however, pHs are considered the smallest component of interstellar dust on the sub-nanometer scale. They can act as catalysts for molecular hydrogen formation and contribute to neutral gas heating via photoelectric effect, among many other things. The presence of pHs has been inferred for a long time now from infrared observations of photodominated regions. And I'm showing an early infrared spectrum here on my slide of the planetary nebula NGC 7027, with its distinctive, quote-unquote, unidentified infrared emission. And this emission is actually caused by pHs. However, at the time in the 1970s, we didn't know that yet. We have since seen this emission toward many other astronomical objects that are photon-dominated regions. The features positioned at 3.3, 6.2, 7.7, 8.6, 11.2, and 12.7 microns can be associated with the vibration modes of pHs. If I'm going through the spectrum here, we can see the pH-CH stretches, the CC stretches, the CH in plane bands, as well as the CH out of plane bands of these molecules in these environments. However, pHs have been only detected as families or a class of molecules until very recently, until 2021. If you want to attempt unambiguous detection of a pH, you have to turn to a very different environment. And we're looking here at an optical image of the dark cloud in Taurus, which is right here. So TMC1 is a well-studied molecular cloud with an inventory of around like 150 known molecules to this day. It's pretty cold and quiescent, and it's also the target of the Gotham survey. So using the 100-meter Robert C. Byrd Green Bank telescope, Gotham's aim is to hunt and find aromatic molecules such as benzene, naphthalene, and pyrene. However, such highly symmetric molecules do not possess a permanent electric dipole moment, so we cannot readily observe them with radio telescopes. Considering a CN functionalized cousin of these molecules, for which the CN group acts like an attached antenna, rotational transitions will be allowed and emission from these molecules can be observed. And this was achieved by the Gotham team fairly recently with the detections of benzonitrile, also called cyanobenzene, in 2018. Shortly after followed cyanonaphthalene in 2021, and more recently cyanopyrene. And since we liked it, we put more rings on it, and we wanted to go look for a larger molecule, the prototypical coronene. But again, we needed to pop on a CN group acting as an antenna to allow for rotational transitions and hence make it radio visible for us. So this is how we come to our molecule cyanocoronene. We first ventured in the laboratory, and this is my main role in the Gotham team, to measure its laboratory rotational spectrum using high-resolution microwave spectroscopy. Once achieved, we can use the lab spectrum to simulate how the emission would look like under TMC1 conditions. And those are low temperatures of approximately 6 Kelvin and applying a shift to of the relative velocity of TMC1. If I overlay this now with our observations of TMC1, which we recorded for 200 hours using the X-band receiver at the GBT, we can identify several individually resolved lines. Some of which are above a 3 sigma level, and I marked them here with asterisks. To quantify the significance of our cyanocoronene detection, we performed a velocity stacked and matched filtering analysis. For this, we extract small spectral windows centered around each of the 100 brightest signal-to-noise ratio cyanocoronene lines in frequency space to produce then a single average line in velocity space. Using the stacked simulated spectrum, which is shown here in orange, as a matched filter now gives us an impulse response of about 17 sigma, which indicates the total statistical significance of our detection. I want to give you a little bit of context in this last minute or so of my presentation, which is really interstellar pHs have strong connections to our own solar system. pHs have been found and analyzed from Ryugu asteroid samples that were returned somewhat recently in December 2020 during the Hayabusa 2 mission. Among the most abundant paths in Ryugu are pyrene and its structural isomer fluorine. Coronene was also detected there. Isotopic composition analysis of such samples delivers insights into the physical conditions under which these molecules must have been formed. But so far, not many low temperature formation pathways have been proposed. Paths were also discovered in other solar system bodies. For example, coronene is the largest pH found in the Murchison meteorite, so without the CN group, among many other pH structures. And lastly, I want to mention the infrared emission that has been seen towards other objects, in particular the 3.3 micron band recorded with James Webb towards some protoplanetary disks and even outside our own galaxy at high Z. So looking at this in the context of star and planet formation, we're basically seeing paths at the beginning and at the end. However, their origin, evolution, and potential recycling is not yet well understood. To summarize, we used high-resolution laboratory rotational spectroscopy and a Green Bank telescope to detect the interstellar 7-ring pH cyanocoronene, the largest molecule detected using radio astronomy to date. pHs present a major reservoir of carbon in space that can potentially be supplied to planets, but their origin and fate remain enigmatic. With that, I'd like to acknowledge the funding we have received and the members of the Gotham team, some of which are here in the room, which is very nice. For this, to me, very exciting combined effort, and thanks to all of you for your attention.
Hold, please. Just to check, seeing it correctly on Zoom and here in the room. Great, Atul, if you want to come. Thank you.
So thank you, AS, for giving me this opportunity. And I'd be talking today about the discovery of the elusive radio burst signatures of massive eruptions in a young active star. Okay. So this is about the stars. So we already heard about the planets and the atmospheres. So we should also worry about the host stars now. So if you look at the stars like our sun, they have a very violent outer atmospheric layer, which often gives out these massive coronal mass ejections, which are hot, energetic, highly magnetized plasma, which are jetted towards the nearby planets, and it can actually impact. This is an example of a coronal mass ejection from our sun impacting the Earth. It's a schematic of that. And you can see how it impacts our Earth's magnetosphere, and it can impact our atmospheres, dumping huge amount of energy into the atmospheres. Luckily, we have a magnetosphere which is sufficient enough to actually guard us from these things, but not every planet may have that luxury. Yeah. So coming to the solar CMEs, or the solar coronal mass ejections, we at NASA's CEDAW data center maintain decades-long database of CMEs and associated Earth impacting phenomena. And this has resulted in over thousands of research papers, and I am glad that I'm part of this group and I contribute to these efforts. And yeah, so when it comes to these CMEs, or these massive coronal mass ejections, as you can see in this GIF, where it propels out into this interplanetary space, producing these strong shock waves and accelerating particles along its way. So what are the observational signatures of these CMEs? So in the radio wave bands, we have these characteristic radio burst types, which are associated closely to different parts of the CME phenomena. For example, this is massive shocks which send out these massive shock waves across the interplanetary space. They create this so-called type 2 radio bursts. And what you see here is actually a radio dynamic spectrum. That's what we call it. Basically, intensity plotted across frequency and time. And you can see this nice drifting burst structure, or intensity drifting structure, which is very closely associated with these massive interplanetary shocks. And we call them the type 2 radio bursts. And associated to that, there are also these type 4 radio bursts, which are actually signatures of high energy electrons in these post-eruption magnetic structures which are attached to the sun. And there are also these energetic electrons and ions which are pushed into the interplanetary space and hitting the planets along these magnetic freeways, if you want to think about it. So they cause something called the type 3 radio bursts, which are these very fast drifting features in the intensity dynamic spectrum. So the type 2, the type 3, and the type 4 are very closely associated with the various phenomenological aspects of the CME itself, and also a strong indicator of CMEs. So now when you come to the other stars, for example, the cooler red dwarfs, why are they more important or more interesting? It's also because they host the most of the known Earth-like exoplanets in the habitable zones. Okay, but at the same time, they are also some of the most strongly magnetically active stars in the galaxy. Okay, they are so strong that the flares, stronger than the strongest ever recorded solar flare, happens every other day or in 2 or 3 in a week. So that's the amount of activity we are talking about. So one would naively expect that, okay, when we observe these stars in the radio band, we should see a lot of these type 2, type 3, type 4 radio bursts every day, or like at least 2, 3 things in a week, right? And people have been searching for this over nearly a decade now, like with various instruments across various stars. And the answer is we don't find any. So that was a mystery. So so here what you see here is basically a typical magnetic field structure of a M dwarf. So we can see these very strong magnetic fields which are threading across the entire star. So what we asked ourselves is like, okay, so why don't we learn from our sun's decades-long database that we have here at NASA with various instruments looking at the sun simultaneously from different vantage points, because different satellites have different orbits around the sun. For example, here you can see the Stereo A, Stereo B. They are two different spacecraft orbiting in a very weird orbit. And there is this Earth-attached spacecraft as well, for example, the WIND spacecraft. So combining all these, you get multi-vantage point observations of the same events. And what we know about the radio burst is that unlike like a optical flare or an X-ray flare, the emission does not reach everywhere. It's more like a laser emission. Unless you are in the beam or the line of sight of the laser, the intensity would drop dramatically, or you can even not detect it. For example, here, there was this flare or a CME which happened, and what you're seeing is actually a dynamic spectrum, which is observed by two different satellites, Stereo A and Stereo B. Both the event actually happened in the visible hemisphere of both the satellites, but the radio observations detected a type 2 and a type 4 only in one case, where it is in the case of Stereo A, where the event happened closer to the disk center. So there is clearly a beaming effect which might be affecting you in the detection. So a non-detection is not always meaning that there is no event. It could be just that you are looking at it in the wrong way. So we wanted to explore this by using multi-spacecraft data of simultaneous observations. And that's what we did using this decades-long database of Stereo A, Stereo B, and WIND space missions. And this is our result in a nutshell. So what you see here is basically the line of sight at which the mission was observing the sun during the event. And you can see like it varies from somewhere around like a 90 plus minus 90 degree longitude. And the colored points are basically denoting the events. So in the x-axis, what we marked in 0 to 20 are the different events observed by the same three satellites. And the colored points actually mark the line of sight along which the best detection happened. And we find that always of the different satellites which observe the same event, the best detection is always within plus minus 60 degree line of sight. So there is a viewing bias to this. So that's the conclusion. And if you are looking for these kind of type 4 radio bursts, you better be aligned towards the active region within plus minus 60 degree line of sight. So now extending these ideas into the stellar realm, we actually checked for stars for which we can be assured that we are kind of pointing at our telescopes at the right line of sight at the active regions. And we chose the star AD Leo, which is a very active star, very young and fast rotating star. And the good point is like our line of sight is right at the active region belt, as you can see here. So whenever a burst happens, we have a right viewing angle that we get a good view into the active region belt, and this is the result. So what you see here is actually a dynamic spectrum from the star AD Leo, and what is below is an example dynamic spectrum from the sun during a very massive CME, which propelled towards the Earth at 2000 kilometers per second. And the correspondence is self-evident, I think. And that's the first case in any active star, and we need more of these using this logic, I guess. Yeah, I'll leave you there. Yeah.
All right. Good afternoon, everyone. It is a pleasure for me today to talk to you about the discovery of bright spots at the surface of this hot, massive blue giant star, Persei. So what you see here is a beautiful image of the California Nebula. And the reason why it is glowing very bright in the red like this is that there is this this star towards the right of it, neighboring star that has a strong radiation that excites most of the particles in the nebula. And that star is Persei. It is a star that's visible in the northern hemisphere. And you can see it actually with the naked eyes. You don't need a telescope or binoculars to see it. It is a hot, massive star. It is about 6 times hotter than the sun and about 26 times more massive than the sun. And I would like to take a little pause here to mention that. So Carl Sagan said that we are the children of stars. And I think what he really meant was that truly we are the children of massive stars like Persei, because stars like the sun don't go supernovae at the end of their lives. It is these massive stars like Persei that end their lives as supernovae. And through that process, they enrich the interstellar medium with new chemical elements that contribute to the formation of new stars and new planetary systems and life on habitable planets like Earth. Yeah, so back to the discovery of bright spots on these hot massive stars. So far, we only have 2 cases where we clearly have evidence of the manifestation of bright spots at the surface of hot massive stars, and those are the cases of Zeta Parpis and Persei. So Zeta Parpis is another hot massive star, well known in the southern hemisphere. And why is this both intriguing and exciting? Well, first of all, because for a very long time, we did not expect, we used to think that these hot massive stars cannot have spots at their surface. And that is because their structures are fundamentally different from the structure of our sun. And yet we see these 2 cases. And so as of now, we don't know what causes them. That's the next step to investigate. So how did we detect these bright spots on Persei? So we used about 13 years of space-based observations using 3 different astrophysics satellite missions to probe variations of light that we receive from the photosphere, from the surface of Persei. So we used the Bright nanosatellite mission, which is a network of 5 working nanosatellites, the size of each, the size of a toaster. We also used the Canadian MOST microsatellite, which is the size of a suitcase. And we used the NASA TESS observatory as well in these observations. So, of course, the pictures that you see here are not to scale, because TESS is about 200 times bigger than MOST, and 20 times bigger than MOST, and 200 times bigger than Bright. So I couldn't represent that here, but yeah, you can imagine. So we took these observations and we applied a time frequency analysis to infer the presence of spots that come and go at the surface of Persei. So what you see in this rather busy diagram is, so towards the top, you see the actual observations of the light variations of Persei as over time, as observed by the BRIGHT mission over about 6 months. And then in the bottom panel, you see what we call a time frequency diagram, which gives the strength of a given signal at any given time. So we clearly detect a 2-day periodicity in these observations. However, as you can see in the time frequency diagram, sometimes that signal is not there at all, like what I'm highlighting here, this portion of the observations where during about 10 days, we just see noisy stuff, no periodicity, and then later we see the 2-day periodicity coming strong for about 8 days. And we also see this behavior in the most observations and in the more recent test observations. Yeah, so that's indicative of rotational modulation caused by the presence of spots that come and go at the surface of the star. So the takeaway is, well, you need to be patient when you do this kind of investigation, but we used 13 years of space-based photometric monitoring of Persei in the optical with most bright and test to detect these bright spots, yet of unknown origins, and which is going to be the next step of our investigation. So yeah, if you're interested, if you have any questions, feel free to send me a message. Yeah, thanks.
All right, Peter, we're going to go to you now online. If you would like to turn on your video and share your slides.
Great. Sounds good. Thank you. Are my slides visible?
Yeah, that looks great here in the room. Thanks.
Great. Yeah, so my name is Peter Craig. I'm a postdoc at Michigan State University. Unfortunately, I couldn't make the trip up to Anchorage this summer, but I'm happy to have the chance to talk to you a little bit about some recent research on a new map of our galaxy in atomic hydrogen that we've been working on over the last couple of years, and I'm really excited to have the chance to talk to you about this today. All right, so first of all, this is an image of a simulated gas disk of the galaxy. This is from a simulation of a Milky Way-like galaxy that has 2 clear spiral arms. And so I have a little animation that shows how this evolves over time during the simulation. All right, so you can see that there's really complex structure that arises in the gas disk of a galaxy like ours. This particular case has these 2 really clear, nice spiral arms that start near the center of this simulated galaxy and move their way out all the way to the outer limits of this gas disk. Between these arms, you kind of get this complex filamentary structure that forms in the gas that we can see here. And a nice map like this of the Milky Way could tell us a lot about the structure and the history of our galaxy. So the basic things like spiral structure in the galaxy, you can draw out from a map of the gas. You can see where the spirals are forming inside the gas disk. You can also use this to study things like warps and ripples that might appear in the disk. So things that come out and into the image here. This is something that astronomers have been working on for a long time. Early maps of the gas disk of the Milky Way date back to the 1950s. And efforts are continuing today to build more and more accurate maps of what the gas distribution in the Milky Way is, and to see what that can tell us about the structure of our galaxy. All right. Now, unfortunately, we live inside the disk of the galaxy, so we don't get a really nice top-down view of the actual disk of the Milky Way, like what we can see in the simulations. Instead, we have an edge-on view from inside, and we have to try to figure out how to build a map like this out of the information that we can get from there. So this is what we actually can get and see in the Milky Way. So what's in this plot is that we see the velocity of the gas along the line of sight. So this is all 21 centimeter emission observed in the radio for neutral atomic hydrogen throughout the galaxy. So on the y-axis, we have the velocity of this, which we can measure with the Doppler shift of this 21 centimeter emission. And on the x-axis, we have the galactic longitude, which is the direction in the galaxy that we're looking. So at the center of the plot, we're looking towards the galactic center. And as we move away from the center, we're looking progressively away from the galactic center until the edges where we are looking directly away from the center of the galaxy. And the colors here represent the amount of intensity of this 21 centimeter emission effectively. So the white regions have more gas and the darker regions have less gas. So the challenge that that we have to solve is how to convert a map like this one, or an image like this one, into a nice top-down view of what the gas actually looks like in the Milky Way, where we can look at what the spiral structure, the warps, and other things in the disk might be doing. So we have a new method to do this. The hard part really is that we need to figure out how far away all of this gas is from us. This is a very common problem, of course, in astronomy, and often a very difficult one to solve. And for the gas in particular, there's really no direct way that we can measure how far away the gas is from us. So what we do that's new is that we are taking the distances to things in the galaxy that we can measure, specifically young stars in the galaxy, and we're using their distances to estimate the distances to the gas. And the young stars in the galaxy are ideal for this because these were born out of the gas relatively recently, and they should be in similar parts of the disk. They should follow similar structures through the galaxy and move in a similar way. So their positions and their velocities are very similar to what we see in the gas. So we can use the distances that we can measure to the stars, which are shown now as red points in this figure, and we can take those distances and assign them to the gas underneath to build nice maps of this gas in the galaxy. So shown here is just a small subset of the selection of stars that we use in our work. We have many more stars than this, in fact, but showing the full stellar sample kind of overwhelms the gas in the background. So this is just a selection of the stars that we have. All right. So here's what our actual H1 map looks like. This is the new map that we've built with our new technique. The first thing you might notice is there's some big gaps in this map in the white regions that look kind of like a keyhole. That's there kind of inevitably with this method because the velocity information that we have for the gas doesn't give us any direct information about the distances to the gas in some parts of the disk. So there are some places where a given velocity that we observe corresponds to multiple possible distances for the gas, and we don't really know where to put it, so we just are leaving those regions blank. So really what we have is a map of the outer parts of the disk of the Milky Way, which we can look for spiral structure and other things that might inform us about the nature of the galaxy and the structure in the galaxy. The next thing that jumps out when you see this map is that the spiral structure that's there does not quite look as nice and well-defined as what we see in our simulations of galaxies. Instead, what we get are kind of these patchy features of higher density gas that kind of traces out a spiral arm-like feature. There are two that are kind of visible here, one on the right side and one on the left side of the image. And here again, the darker colors show lower densities and the brighter colors show higher densities. So there's a couple of kind of patchy high density regions here, and as you move farther out in the disk, the density falls off. So the structure that we're seeing in the Milky Way is very flocculent and patchy compared to what we see in the simulations and compared to maps of this gas disk that have been generated using other methods before. So the spiral structure we see shorter spiral arms, and they're not as well defined, and they're a little bit kind of fuzzier and patchier than what we've seen in other maps of the galaxy. So the main takeaways, so we can use this new map of the Milky Way to better understand the structure and the spiral structure in particular of the gas disk of the galaxy. It appears to be the case that the gas disk is probably more flocculent with smaller arms that are patchier in nature than was previously believed. In the future, we expect that a map like this one might be able to be used for characterizing the dark matter in the galaxy, because the motion of this gas around the galactic center can help to inform about the distribution of dark matter in the galaxy and that kind of thing. So there are some really exciting future prospects for this kind of map, and all kinds of cool things that we can learn about the galaxy and the distribution of material throughout the Milky Way. If you have any questions, feel free to contact me. My contact information is here and will be in the, yeah, it will be available in my slides. Yeah, I'm happy to answer any questions that you have.
All right, thank you, Peter. Just going to switch back to our in-person mode here quickly. Just trying to move this bar out of the way for you, but I've lost the mouse. Nope. All right. I think it lives there. I don't think it's cool.
Okay, hello everyone. It is my pleasure to present this exciting result. I am Wanggi Lim from Caltech IPAC, supporting Roman the telescope project, and then Jim Dubaiser at SETI Institute is the PI of the project. The background image is the four-color image of the Galactic Center regions with Spitzer, SOFIA, and Herschel, which we used in this study. I will get back to this image after going through some necessary background information. So let me start with the main takeaway of this study. Here we present the best and the last view of ongoing star formation activities in the galactic center. And then such data will not be replicated within the foreseeable future. And then we also show that the galactic center massive star forming regions do not follow the traditional scientific category. All right, so here are the background. The galactic center of this study means the inner 1,600 light year area around our galaxy supermassive black hole. And then the regions show that about like 100 times higher gas density than the other galactic plane where our sun is. But the star formation rate is 10 times lower than the other galactic plane. Also, the very active star formation activity, which is called as a starburst, happened at least 10 million years ago, and the current massive star formation activity is very rare and then very difficult to find. Giant H2 regions are large ionized gas clouds, and the massive young stars in the cloud are assumed to be in charge of those ionization. And then these giant H2 regions are also bright across almost all wavelengths. So the giant H2 regions are kind of almost the only detectable substructures of external galaxies. Okay, here are some observations. The image on the right is mid-infrared and then radio combined image toward inner 1,600 light year location. And then as you can see, the mid-half area is bright across the mid-infrared wavelengths. And then this mid-infrared bright structure was observed by SOFIA 25 and 37 micron band. All right, so here we get back to the other SOFIA image, and then let's move to the detail. So as you can see from the labels, both Sagittarius B regions on the left and then Sagittarius C region on the right are about 300 light years away from the galactic center black hole. And then I want you remind that the colors of these images are written on the far right side of the slide. And then white background stars are from Spitzer 3.5 micron, and then blue and green colors are from SOFIA 25 and 37 micron respectively. And then the red color shows Herschel 70 micron map. And then you can simply think blue traces warmer dust, and the red traces cold dust. And the red point sources imply very young stellar objects surrounded by cold dust, which could not have enough time to hit it by the other center stars. Okay, so let's zoom into that each individual target. All right, so here is Sagittarius B regions. So between B1 and B2, only B1 was identified as a giant H2 regions, showing very bright mid-infrared flux, and was assumed to have a massive young stellar object that are hitting actually native clouds. But it is difficult to find red point sources, and then SOFIA band colors seem to be very dispersed. So this indicates that the high mid-infrared flux may come from the externally heated dust by nearby old massive stars, not really young massive stars. And then, but like B2 is full of red compact sources that indicates there are active star formation activities situated in there. Okay, this is Sagittarius C, and then it shows similar features with Sagittarius B1, and then therefore the location may not show very active massive star formation activities. You may recognize a couple of red point sources around the center, but they do not seem to be powerful enough to ignite all these entire Sagittarius C location. Sorry. So here I compare the properties we found for Sagittarius B1, B2, and C with the other Galactic plane, giant H2 regions. And then even though B2 was not classified as a giant H2 region in previous studies, it is only location alike Galactic plane, giant H2 region. And then there are also observational indication of star formation activities, such as various major emissions toward the other B2 region. Sagittarius B1 and C are opposite. So they are defined, they were defined as the giant H2 regions before, but the indication of star formation activities are not like Galactic plane, giant H2 regions. Okay, here is the last summary slide. So we showed the best and the last mid-infrared view of star formation activities in the galactic center. And then we may not be able to replicate such data within any foreseeable future. Sagittarius B1, B2, BC, all of them may need to be reclassified, and this may also indicate that fellow astronomers need to work on reassessment of the other massive star forming regions in the extreme environment, like our Caltech Center. And then again, my name is Wanggi Lim, and then Jim DeBiser is a PI of this project. Thank you.
All right, we will shortly get set up for our Q&A portion. Just going to bring Peter back to the screen quickly. All right. Okay, we should be all set there. Okay, so for our Q&A here in the room, our Astrobites media intern, Lucas Brown, is going to bring the microphone around. Please remember to state your name, your affiliation, and who your question is for. And that goes for our online folks as well. If you could please include that information when you type your question into the Q&A feature. All right, let's start with questions here in the room. Ethan.
Hi, thank you to the whole panel for a series of really excellent and interesting presentations. My question is for Peter. Peter, you talked about how you were doing this 21 centimeter mapping, particularly near the center of the galaxy, and you mentioned that this could be useful for understanding the distribution of dark matter. And I didn't quite see the connection there. Can you elaborate a little bit on how this technique can reveal things like the presence and density distribution of dark matter?
Yeah, absolutely. That's a great question. Yeah, so one of the main tracers that we have for understanding the distribution of dark matter in the galaxy is by looking for the impact of its gravity on the material that we can see distributed throughout the Milky Way. So maps like this, they give us an idea of the structure and the motion of material in the disk of the galaxy can be pretty useful for trying to constrain the gravitational effects of the dark matter that's underlying all of this. Yeah. So also point out our map. So we lose data in the center of the galaxy, unfortunately, because we can't measure distances accurately there. So most of our data is at the outer edges. So we get kind of an idea of what the dark matter mass might be like in the interior of the galaxy, but we lose out on detailed information on the interior.
All right, further questions here in the room? Want to take one from online? Okay.
Okay. Can people, yes, this is coming through the room. All right. I also have it in my ear. Okay. So there are one question from online from Monica Young from Sky and Telescope is also for Peter. So she is asking if the flocculent structure in the simulation shows bubbles forming, and we often associate that with stellar feedback, like stellar winds and supernovae. Are bubbles also a natural product of spiral arm formation or other gas instabilities? And is the result saying that the flocculentness in reality is patchier than the more organized bubble-like structure in the simulation?
Thank you for the question. Yeah, so I believe that that the bubble formation that you see in the simulation likely does involve some degree of star formation activity that's responsible for a lot of the bubbles that you see forming there. That's probably the dominant source in that case over the spiral structure formation. I think that if you set up a similar simulation that doesn't include any kind of star formation or related feedback mechanism, then you'll see that a relatively smooth spiral structure forms without the same level of bubbles forming in the disk. Yeah. What was the second part of that question again?
The second part of the question is the result saying that the flocculentness in reality is patchier than the more organized bubble-like structure in the simulation?
Okay, thank you. Yeah, so our results do seem to show that the patchiness that we see in the actual gas disk is quite a bit more than what we see in the simulations. So inside our simulated galaxy, we see these smooth, pretty continuous arms that are surrounded kind of by these bubbles that maybe are being formed by some kind of stellar feedback mechanism. In our maps of the disk, the arms themselves have small gaps and large variations in density just along the arm that are probably a bit larger than what you would expect to come out of just the star formation feedback into the disk. And also we see that the degree of flocculentness that we see in our maps is a little bit larger than what we've seen in other maps of the H1 disk. So we think that our new technique for measuring distances that we think is a little bit more accurate, or a little bit better at least at capturing small scale features in the disk, seems to show that the arms are a little bit more flocculent than we thought before.
All right, I've got a question. This is Kerry Hensley from the AAS. I have several questions actually, and my first one is for Gabi. So do you expect to find polycyclic aromatic hydrocarbons with even more rings, either in the cloud that you've studied or in other interstellar clouds, other galaxies even? And if so, what steps would you need to take in order to discover those?
Yeah, thanks so much for the question. Yes, indeed, we want to put more rings on them, and we would like to detect other pHs. So I can answer this twofold. We would like to push the limits of the field detecting larger and larger molecules with radio astronomy, because we do have in the rotational spectrum those fingerprints that let or allow us to identify the molecules unambiguously, which is of course a great advantage if it comes to molecular detection in space. We are also striving to look for the pHs elsewhere outside of dark molecular clouds. I would like to highlight another survey that we're running, which is called ARCHM, which has looked for benzonitrile outside of TMC1, and it has been found in many other sources. And we do expect the pHs to be there in those sources as well. So we would like to point the GBT towards those sources in the future as well. We have recently been granted some more time as well to look for pHs in photodominated regions. So this will be a very interesting step for us as well to take to see if these pHs can actually survive the harsh interstellar environment of PDRs in their size that we're currently seeing them. And to answer your question from the lab side, to take more laboratory spectra will be absolutely critical for us to be able to actually search for the astronomical signatures of these pHs.
Great, thank you. Any questions from anyone else in the room before I keep going? All right. Any online, Lexi? Okay.
Okay. So this is a question for Tahina. Hopefully I pronounced that correctly. And this is from Jean Malone. And the question is, does spectroscopy of this bright star indicate compositional anomalies in this star, as in the peculiar A stars?
Yeah, thanks for the great question. So Persei and Zeta Purpis are known to be not chemically peculiar. Unfortunately, that would have been the easiest explanation, actually. But yeah, yeah, they are relatively bright stars, so it's relatively easy to get good quality spectroscopy to verify it. And yeah, all past studies with tons of spectra do not indicate chemical peculiarity. So yeah.
Great, thank you. Other questions online or in the room? Lexi's nodding. Yes, okay.
We have another one for Peter from Bill Waller at the Galactic Inquirer. How many stars did you access and where did the data come from?
Yeah, so our stellar sample has just under 38,000 stars all told. These are distributed throughout the outer parts of the galaxy. Most of them are relatively nearby because that's where we have good data, but some of them are out on the far side of the disk as well. Most of our data is from the Gaia Space Telescope. It's a really good source for getting accurate distances to stars distributed throughout the disk, and there's a tremendous number of stars that are available there. But we do have some data that's mixed through an assortment of other places, mostly for things like Cepheid variable stars, which give us an alternative mechanism to measure distances, and some additional sources to get velocity measurements as well, as need be. But Gaia is definitely the bulk of our data.
All right, I have a question for Atul. So it's very exciting to both figure out why we haven't seen something for a whole century and then to find evidence for that thing. So I'd just like to know what is next. Are there particular data sets or observations that you are looking to do next, or is this more in a modeling phase now to figure out more about these mechanisms?
Yeah, so it's both, I would say. So we need actually more multi-waveband observations to make a good model of, like what is going on in the surface of the star. Yeah, we did find the signature, but we also found that the emission mechanism is quite different from what we have in the sun. So the active regions in these stars are actually very different from what we know of the sun in terms of its magnetic field strengths, and also hence the emission mechanism. But if we want better constraints on that, we need also like X-ray and spectroscopic observations using various space missions. And actually we are doing a campaign like that with combined multi-waveband observations using radio to X-ray. And that would give us more sense about how they are different. And then the other thing is also yeah, we got one, but that's not it, right? I mean, the same star, we have to monitor more to get a rate of these events so that we can have a sense for what is the energetic particle flux. And that affects a lot of the chemistry that's going on in the planetary atmospheres and so on. So yeah, that's the next.
Awesome. Thank you so much. I have a question also for Wanggi. So obviously, extremely unfortunate that SOFIA has been decommissioned.
Right.
I feel like every question for a SOFIA talk starts out that way. So in absence of further SOFIA observations, are there complementary data or other data that you're looking to collect to study these regions?
So that's why I actually called these data will not be replicated in foreseeable future. But hopefully we can actually process with the PRIMA, which is actually the probe mission of the mid-infrared and the far-infrared observations. So in case we have the PRIMA, then we probably can actually reflect replicate this data within probably in 2 decades or something. But like right now, JWST is the only facility that can actually kind of like imitate like this kind of observation, but like wavelength range is also limited. And then JWST is not designed to actually observe really large like survey things. So that probably is not really a wise way to use the JWST.
Thank you. All right, one last call for questions here in the room or on Zoom. If not, we can finish up there. So thank you so much, everyone, for your attendance and your attention. Thank you to our speakers, as well as the public information officers who assisted with preparation. We are going to be back here again tomorrow morning at 10:15 for another press conference on planets, exoplanets, and brown dwarfs. I hope to see you all here then, and let's finish with one last round of applause for our speakers.